So, in the last class we saw about the reduction of a context free grammar. So, how to remove the epsilon productions, the unit productions, and how to remove the useless non-terminals. We also saw what is a Chomsky normal form and what is a Greibach normal form, and how to convert a context free grammar into Chomsky normal form if it does not contain epsilon. Of course, for epsilon we saw that if you want to include epsilon, then we should have a rule of the form S goes to epsilon and S does not occur on the right hand side of any production. Now, we shall see how to convert a grammar to Greibach normal form. For that we saw two lemmas. We will be making use of these two lemmas. Let us recall those two lemmas. Lemma 1 says that define an A production to be a production with a variable A on the left, and if you have a grammar G is equal to NTPS, then for some reason if you want to get rid of the rule A goes to alpha 1 B alpha 2, where alpha 1 and alpha 2 are some strings, then instead of this you have to include a set of rules. With B on the left hand side, the set of B productions are B goes to beta 1, B goes to beta 2, B goes to beta R. Then this rule can be replaced by a set of rules where you have that is, you remove this rule, but instead add the rules A goes to alpha 1 beta 1 alpha 2 alpha 1 beta 2 alpha 2 and so on. So, instead of these R, instead of this rule, you have add R rules of this form. The effect will be the same, because if you apply this rule and afterwards you apply a rule B goes to beta I, then the effect of applying this and then B goes to beta I is achieved by using the rule A goes to alpha I beta I alpha 2. So, the language generated will not be affected, it is the same, but the only advantage you have got is you have got rid of this rule. Let us see why we need that when we convert the grammar into Greibach normal form. The next dilemma is to avoid left recursion. This we have seen. Again, let G be a context free grammar and A goes to A alpha 1 A alpha 2 be a set of left recursive rules with A on the left hand side, and A goes to beta 1 beta 2 beta are the non left recursive rules with A on the left hand side. Then this R plus S rules can be replaced by 2R plus 2 rules of this form. A goes to beta I, A goes to beta I Z, where Z is a new non-terminal introduced and I varies from 1 to S, and Z goes to alpha I, Z goes to alpha I Z, 2R rules. So, the R plus S rules are really replaced by 2R plus 2S rules. In order when we do this, the left recursion is removed, but a right recursion is introduced, but the language generated is not affected. This also we have seen. So, we will make use of these two lemmas to convert a given grammar into Greibach normal form. So, let us take the simple example. We started with a simple example. S goes to ASB, S goes to AB, the language generated is A power n, B power n. So, for convenience we can take languages which do not contain epsilon. So, the first step will be like in Chomsky normal form, every terminal symbol will be replaced by a non-terminal symbol. So, S goes to ASB, S goes to AB will be replaced by S goes to ASB, S goes to AB, where A and B are new non-terminals introduced, A corresponding to small a and B corresponding to small b. Now, this small capital A goes to A, capital B goes to B will take care of the fact that these A and B are ultimately converted into small a's and b's, which are terminal symbols. We can very easily see that this grammar generates A power n, B power n, this also generates A power n, B power n. Initially it generates capital A power n, capital B power n, then all the A's are made into are converted into small a's and all capital B's are converted into small b's. So, the language generated is not going to be affected. That is the first step. Then the second step is among the non-terminals you introduce an ordering, call them as A1, A2, A3. So, in this example, for example, you can take S to be A1, A to be A2 and B to be A3, then the rules will be of this form: A1 goes to A2, A1, A3, A1 goes to A2, A3 and then A2 goes to A, A3 goes to B. This is, you introduce an ordering among the non-terminals. Again, this is just renaming of non-terminals, so the language generated is not going to be affected. Now, after doing this, the third step is use lemma 1 and 2 and convert the rules in such a way that at the end of this step the rules are of the form in GNF are of the form AI goes to AJ some gamma where J greater than I. You may also have some Z rules, that is the Z's are the new non-terminals introduced. So, you use lemma 1 and lemma 2 in an appropriate manner, which we can take an example and see, and at the end of this step either the rules will be in Greibach normal form or the AI rules will be of the form AI goes to AJ gamma where J is greater than I. That is the first symbol on the right hand side, the AJ is such that J will be greater than I. When you do this, you may introduce some Z rules also. Z is the set of Z1, Z2 you may be introducing. Let us see how to do this. For this you go from actually A1 to AN. First you convert the A1 rules, then you convert the A2 rules and so on. Actually in the example which we have considered, this step is not necessary. Look at the rules at the end of the second step. A1 goes to A2, A1, A3, this is 2 is greater than 1, A1 goes to A2, A3, this is greater than 1, A2 goes to A, A3 goes to B are in Greibach normal form. So, the third step in this example is not necessary. Some other example it may become necessary. Then the fourth step is convert the AI rules into Greibach normal form. In this step you will go from AN to A. First you will see the non-terminals are A1, A2, AN. Then by this condition the last one AN rules will be in Greibach normal form, because you cannot have something greater than that on the right hand side. So, at the end you will find that the AN rules will be in Greibach normal form. So, make use of them in AN minus 1 rules, then make use of them in AN minus 2 rules and so on, keep on back substitute, and at the end of the fourth step all the AI rules will be in Greibach normal form. So, let us take this example which we have been considering. Look at this rule. You have to, the fourth step you have to go from an to a1. So, look at a3, this rule is in Greibach normal form. Look at a2, this is in Greibach normal form. The a1 rules are not in Greibach normal form. So, you have to convert them to Greibach normal form. Use the lemma 1. So, you want to get rid of this rule. So, instead of a2, wherever there is a a2 rule, you have to use them, right. That is lemma 1. Instead of a2, you use this rule. That means, instead of this rule, you will be writing a1 goes to small a, a3. Similarly, in this rule, use lemma 1, you get rid of this rule, but substitute for this a2. a2 goes to a is a rule you are having. So, here also this a2 you will be replacing by the right hand side, that is a. So, these two rules will be replaced by replacing the a2 by a. So, this example, the fourth step becomes a3 goes to b will be there, a2 goes to a will be there, then a1 instead of a2 you write a, a1, a3, a1 goes to a, a3. Now, throughout the conversion either you will be using lemma 1 or lemma 2, and we have already seen that those two lemmas, the language generated is not affected. Now, you find that this grammar is in Greibach normal form. This rule, on the right hand side you are having only a terminal symbol, these two rules you are having a terminal followed by a string of non-terminals. So, the grammar has been converted into Greibach normal form with these four rules, but you can easily see that this useless symbol a2 is an useless symbol now, because a2 we have already replaced. So, this rule is useless and symbol is also useless. So, 1, 2, 3 rules are enough. After conversion you may end up with some useless symbols, useless productions. You can remove them in the usual way. So, this is the fourth step. The fifth step, which is not necessary in this example, is convert the Z rules into GNF. By the way the Z rules are, they will be of the form Z goes to some AI something Z in the end Z, or Z goes to some AI, they will be of this form. The first symbol will not be a Z anyway. So, again making use of lemma 1, at this stage all the AI rules are in Greibach normal form. So, make use of them and make, instead of this AI, put the right hand side of those rules. So, in that case all the Z rules will be converted to Greibach normal form. In this particular example it is not necessary, at the fourth stage itself it is converted into Greibach normal form. Let us take one more example where this fifth step will be necessary. So, let us take a almost similar example. What is the language generated? The language generated is the Dyke set, which is the well formed strings of parenthesis. Now, let us convert these, the earlier one we had only these two rules, now we have one additional rule S, S goes to SS. So, the first step is, what is the first step? For every terminal symbol, introduce a new non-terminal. So, the rules will become S goes to SS, S goes to ASB, S goes to AB, A goes to A, B goes to B. This is the first step. Then the second step is introduce an ordering among the non-terminals. So, make S as A1, A as A2, B as A3. So, the rules will become now A1 goes to A1 A1, A1 goes to A2 A1 A3, A1 goes to A2 A3. Wherever you have S you have put A1, wherever you have capital A you have put A2, wherever you have capital B you have put A3. Then these rules will become A2 goes to A, A3 goes to B. Now the third step becomes necessary because the condition that Ai goes to Aj where j is greater than I is satisfied by these two rules, but not by this rule. This rule, left hand side you have A1, right hand side also the first symbol is A1. So, you have to use something to convert this. Now, what do you do for that? Now, you note that this is a left recursive. Which one you will use? Sometimes you have to use lemma 1, sometimes you have to use lemma 2. At this stage, to convert the A1 rules in such a way that the first symbol on the right hand side is A2 or A3, you have to use a lemma 2 because there is a left recursive rule. A1 goes to A1, the first symbol is again the same as A1, so there is a left recursive rule. So, how do you go about doing this? Now, you have A1 goes to A1 A1 as a left recursive rule, and the left recursive rules are A1 goes to A2 A1 A3, A1 goes to A2 A3. In the lemma if you put alpha 1 is this, beta 1 is this, beta 2 is this. So, there is 1 plus 2 rules here. Instead, we have to replace them by 2 plus 4 rules, 6 rules. So, what are they? The rules are A goes to beta I and A goes to beta I z. So, you will have A1 goes to, you will be introducing the new non-terminal z. So, A1 goes to A2 A1 A3, A1 goes to A2 A3, this is of the form A goes to beta I. Then you have A1 goes to A2 A1 A3 z, A1 goes to A2 A3 z. So, instead of these 2 rules you are getting 4 rules. Now, instead of this one rule you must get 2 rules. What is alpha 1? Alpha 1 is this A1, not this together, A1 alpha 1, is not it, left recursion. So, alpha 1 is A1, so the rules will be of the form z goes to alpha 1, z goes to alpha 1 z, but what is alpha 1 is A1. A1 So, instead of the 3 rules we have 6 rules. Apart from that, the other 2 rules will be there. A2 goes to A, A3 goes to B. So, at the end of step 3 we have 8 rules. The AI rules satisfy the condition that they are of the form AI goes to AJ something, this is 2 is greater than 1, 2 is greater than 1 and so on. Here they are in Greibach normal form. Okay, apart from that we are having 2 Z rules also. Now, the step 4 you convert the, see in step 3 we have gone from A1 then A2 then A3. A1 we have done so that it is converted into the required form. A2 and A3 are already in Greibach normal form, so we need not have to do anything about that. In step 4 we have to convert all the AI rules into Greibach normal form. For that first we start with A3, then A2, then A1. So, at the end of step 3 all the AN rules will anyway be in Greibach normal form. So, see A3 will be in Greibach normal form, A2 also is in Greibach normal form. Now, we have to convert this into Greibach normal form. Again for this which one you will use, lemma 1 or lemma 2? Lemma 1, because on the right hand side you are having A2, this could be easily replaced by the small a. So, in each of these 4 rules you can replace A2 with A. So, at the end of step 4 A3 goes to B will be there, A2 goes to A will be there, then A1 goes to A, we will see the rules and then write. A2, A1, A3, A1 goes to, instead of A2 you write A, A1, A3, A1 goes to A, A3, A1 goes to A, A1, A3, Z, A1 goes to A2, A, A3, Z. The 2 Z rules will be there, Z goes to A1, Z goes to A1, Z, those 2 rules will be there. So, at the end of step 4 you have these rules. Now, note that all the AI rules have been converted into Greibach normal form. Step 5 is to convert the Z rules to Greibach normal form. So, step 5 these 6 rules will be there. Maybe I need not write them again. These 6 rules will be there. These red rules we have to convert to Greibach normal form. Again you have to use lemma 1, this for this A1 you have to substitute from these 4 rules, right, whatever is on the right hand side. You want to get rid of this rule. So, Z goes to, instead of A1 use these right hand sides, Z goes to A1 Z, instead of A1 use these right hand sides. So, you will get Z goes to A, A1, A3, Z goes to A, A3, Z goes to A, A1, A3, Z, Z goes to A, A3, Z. Now for this rule if you do the same thing you will get Z goes to A1, A3, Z, Z goes to A3, Z, Z goes to A1, A3, Z, Z. For this A1 I am substituting all these 4 right hand sides. Z goes to A3, Z, this Z comes here. So for this A1 you can substitute all the 4, for this A1 also you can substitute all the 4, so you get 8 rules. But note that this is the same as this, it is getting repeated. These 2 rules are repeated, so you need not have them. It is the same. So at the end you are getting 6 plus 6, 12 rules. Now look at these 12 rules. At the end of 5th step you are having 12 rules. These rules are all in Greibach normal form. These rules are also in Greibach normal form. So you have converted the given grammar into Greibach normal form. So the steps involved in conversion to Greibach normal form are: first step will be for every terminal symbol introduce a new non-terminal symbol, then rename the non-terminals and introduce an ordering among them, call them as A1, A2, A3. This is just to bring the AI rules into Greibach normal form. Then the third step you can use lemma 1 and lemma 2 and convert the rules in such a way that at the end of the step you will all the AI rules will be of the form A goes to Aj gamma where j is greater than I. While doing this you may introduce some Z symbols, new symbols you may be introducing. And in this step first you will convert the A1 rules, then the A2 rules, then the A3 rules and so on up to the nth rules. At the end of this step all the AN rules will be in Greibach normal form. So in step 4 what you do is convert the AI rules in the Greibach normal form, for which you will go from AN to A1. First you look at the A1 rules, then AN minus 1 rules and so on. So at the end of step 4 all the AI rules will be converted into Greibach normal form, but the Z rules may not be in Greibach normal form. So the 5th step is use again lemma 1 to convert the Z rules into Greibach normal form, use substitution. So this is what we have done in this example. So at the end this is converted into Greibach normal form. The language generated is not affected. See, it is easy to see in this example. Look at this example, this one, this is the Dyke set. It is easy to see that it generates a Dyke set, is not it? It has got three rules and it is very simple. Whereas at the end you are ending up with the 12 rules, and by looking at these 12 rules there is no way you can immediately say that it is the Dyke set, is not it? You will not know what is the language, it is it's slightly complicated. So, but how can you prove that the language generated is the same as the earlier one? Because throughout the conversion what have you used? You have used only lemma 1 and lemma 2, nothing else. And we have already shown that if you use two lemmas, those two lemmas, the language generated is not affected. So at the end you end up with a Greibach normal form which generates the same language. Now what is the advantage? Why should you convert something into Greibach normal form? As I told you, the thing is it is easier for parsing, and when we want to show the equivalence between push down automata and context free grammar, taking the grammar in Greibach normal form helps. Also, when you write a grammar for a compiler, as far as possible if you write the rules in Greibach normal form, that parsing portion will be easy, the construction of the table will be easy. So, we have seen two normal forms. Two normal forms, one is the Chomsky normal form and another is the Greibach normal form. There are other normal forms, something is called operator precedence normal form, binary standard form, there are other things also, but we will not go into them. Each one has its own advantage, because something will for some theorem that may be helpful and so on. Even Greibach normal form, for proving some theorems, if you assume that the grammar is in Greibach normal form, it is very easy. We shall see where it is used in due course. Now, coming back to ambiguity, we have seen what is an ambiguous grammar, what is a ambiguous language, what is an inherently ambiguous language and so on. So, let me take this example which we have already considered. S goes to AB, S goes to BA, B goes to B, B goes to BS, B goes to A, B, B. This example we considered earlier in the class. A goes to A goes to AS, A goes to BAA. The language consisted of strings having equal number of A's and B's. Epsilon is not included. Is this grammar ambiguous or not? Consider the string AA, BB, AB. You can see that this particular string can be generated in two different ways. Start with this S. Now, there is one thing which we will make use of later. See, when you have a S and a combination, that is S you have, and you have to generate the tree in a top down manner now. When you have an S and A, you must use this rule. When you have S and B, you can use only this rule, that is fixed. Similarly, when you have a B and A, you can have to use this rule, but if you have a B and B, you can use either of them. Okay. If the non-terminal and the first symbol, they tell you by looking at the first symbol in this, if you are able to say which rule is to be used, then such a grammar is called a LL1 grammar, and that is very useful in recursive descent parsers. This is not LL1, I will have the problem. But S and A combination, this is the string to be generated. So, first you have S and A, so you have to use this rule. Then B and A, next symbol to be generated is A, so you have a B and A combination, so you have to use this rule only, A, B, B. But for this B, you can either use B and terminate, or in another way, these two steps are the same. You can use BS here. Then from this B, you have to generate BAB. So, you will get BS, A, B, B. Now here from this S you have to generate a B. So, B A, this will go to A, this will go to B. So, the string generated is AA B AB, here also AA BB AB, but the derivation trees are different. So, this grammar is ambiguous, but this language is not inherently ambiguous. You can give an unambiguous grammar for this. We can consider how to give an unambiguous grammar like this. Now, the first, as I told you at this stage, first two steps are the same. You generate AA and then capital BB, AA BB you generate. Then from these two B's you have to generate this. We know that if a string is derivable from S, it has got equal number of A's and B's. If a string is derivable from B, it has got one more B than it has A's. If a string is derivable from A, it has got one more A than it has B's. Now, from this B, you have to derive a string which has got one B more than A, and from this B also you have to derive a string which has got one more B than it has A. Now, this BBAB portion you can split like BBAB. That is, this also has one B and 0 A's, and this has got 2 B's and 1 A's, or you can split it as BBAB. This portion will have 2 B's and 1 A's, this has 1. So, this BBAB you can split in two ways, two substrings, each one of them having 1 B more than the number of A's, and because of that possibility, this derivation from BB is done in two different ways. Now, if you want to construct an unambiguous grammar, you must avoid that. Just think about how to do that. Now, as in expressions, like you have E goes to E plus E, E goes to E star E, E goes to E, E goes to identifier. Now, let me take the identifier, okay, identifier will keep it as it is. So, expressions of the form ID plus ID plus ID can be generated by this, but they will be ambiguous. You can have two different derivation trees, like E goes to E plus E, E plus E, ID, 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 or E goes to E plus E, this goes to ID, this again goes to E plus E, and this goes to ID, this goes to ID. You can have two different derivation trees, and so there will be problem. But if you keep a method that you will have to have only the leftmost, that is, first this has to be, the evaluation is from left to right, then this will be performed first and then this will, with the result this will be added, right. So, actually this is the one that will be taken, these two will be added first and with the result this will be added, this will not be taken. If the evaluation is from left to right, you have to do that. If you have something like ID plus ID star ID, then E goes to E plus E, E star E, then E goes to identifier, identifier, identifier. you can also have E goes to E star E, E goes to identifier, E plus E identifier, identifier. Which one we will consider? Here even if you take the evaluation from left to right, usually star has a higher precedence. So, this will be performed first and then the addition. So, this tree will be taken and not this tree. So, you can have that grammar and have this set of a thing, that is the evaluation has to be from left to right and then there is a precedence among the operators and so on. And you want to override the precedence, use the parenthesis. But you can write it the same effect by considering, see this is a term and then each one is a factor. So, instead of having those rules, you can have a set of rules of this form. E goes to E plus T, E goes to T, expression plus term, because the evaluation is from left to right, you always have expression plus term. T goes to term, okay, I will remove this rule. T goes to T star F, T goes to F, F goes to E, F goes to it. F is factor. So, what will be the derivation tree for the two things? If you have E plus R, I mean I would ID plus ID plus ID, you will use E goes to E plus T, then again E plus T, T goes to F, F goes to ID, T goes to F, F goes to ID, here E goes to T, T goes to F, F goes to ID. This will be the only derivation tree and this makes sure of the left to right evaluation process. Then when you have that ID plus ID star ID, what sort of a derivation tree you will have? E goes to E plus E, this E goes to E plus sorry E plus T, T goes to T star F, E goes to T, T goes to F, F goes to ID, T goes to F, F goes to ID, F goes to ID. This is the only way you will have, you cannot have it in another way. So, for every string of this form or whatever form it is involving identifiers and the operators plus or star, there will be a unique derivation tree. This grammar which consists of this makes sure that the evaluation is left to right. Here also because of this the evaluation, if you have continuous star, the evaluation will be ID star ID star ID, the evaluation will be from left to right. But then star will be performed first before the plus is because the term is evaluated first, T star F, your E is the highest one, then from that expression you go to term consists of factors. So, expression consists of terms and the terms will be evaluated from left to right. terms consist of factors, factors will also be evaluated from left to right, but factors are evaluated, then terms are evaluated, then expression is evaluated. That gives the priority operation is taken. Star has higher precedence than plus, that is taken care of. So, you can split this in such a way that you get an unambiguous grammar, and this grammar has 6 rules. So, you see that this is an unambiguous grammar, and it is very convenient to use this unambiguous grammar for generating the arithmetic expression, because that is very convenient, and for code generation also that will be very useful. So, you can convert an ambiguous grammar into an unambiguous one, provided the language generated is unambiguous. You can see, if you have an inherently ambiguous grammar, whatever grammar you give, it will be ambiguous only. But if it is an unambiguous language, you can convert an ambiguous grammar to an equivalent unambiguous, give an unambiguous grammar for a ambiguous grammar. But in this example, you have analyzed how the strings are formed, and in the compiler what do we do? The evaluation will be from left to right, and star will have a higher priority than plus. So, we were able to give an unambiguous grammar. This any grammar means you have to look into the problem. There is no hard and fast rule that you have to go like this step by step. In Greibach normal form, it was a step by step procedure. It is a very straightforward, you do this step first, do this steps again, and so on. Now, if you want to convert an ambiguous grammar into an equivalent unambiguous grammar, it is not a straightforward procedure. Each problem you have to look into that problem and see what can be done, convert this way, that way, and so on. Okay. So, this is the way you can do. There are, as I mentioned, inherently ambiguous languages like a power n, p power m, c power k, n is equal to m, or m is equal to k. Such languages are inherently ambiguous. We have already noted that given a context free grammar, it is undecidable whether it is to find out whether it is ambiguous or not. But if a language is a bounded language, what is a bounded language? There are fixed words W1, W2 like that, WK, fixed words such that the language will be of this form, I1, I2, IK, they are integers having some relationship. Now, if the language is of this form, it is called a bounded language, and given a bounded language, there are algorithms which will tell you whether it is inherently ambiguous or not. If L is a bounded language, bounded CFL, there exists an algorithm which tells us L is inherently ambiguous or not. But we will not go into the details of the algorithm, it involves some other definition, some other concepts, and so on. So, this is a result which we will take for granted.